All right, we got quite a few people here. Let's start rolling. 7 o'clock. Again, thank you everybody for coming out and spending an hour with me this morning. We're going to be covering airflow diagnostics today. We are covering kind of the basics. If there'll be a survey at the end, if you want to go deeper dive into airflow, go ahead and leave a comment in the surveys and let us know. That's something you'd like to know more about. Also visit fieldtechhelp.com, which I'll have that posted at the I'll have that posted at the end of the slide deck so you can copy and paste that Field Tech Help. So this morning, first thing, if you do not have Gensco Tech Services, this is 253-620-8282. That is good for Trane, American Standard, and Mitsubishi product. Save it to your phone right now. Fastest way to get a hold of us. Take a picture of that data plate that you're working on, text it in, give us your name and company. You're going to get built in the system, so next time you won't have to repeat yourself. Give us a brief description of what you got going on. You get built in the queue. We try to get to everybody within 20 minutes, but some days are heavier than others, so we appreciate your patience. Just try to give us as much information. We're from the field, so we'd like to see pictures. Give us a picture of that installation while you're waiting for us to call back, right? Anything that you might think is the issue, let's go ahead, send that picture in. When you're in there digging into the wires and whatnot, give me a picture of what the wires you're working on, because I don't have all those colors of wires committed to memory. Not yet, anyway, working on it. So again, we appreciate your patience. We try to get to everybody within 20 minutes. I am the Western Washington North FSR Jamin Meyer. I've been in the field over 20 years, from doing crawl space work to a little bit of high rise, lots of commercial. So I got a good extensive background to me, and I'm here to give you guys as much information and share my knowledge and experience to hopefully speed you up and eliminate some questions and concerns in the field. So again, reach out to Tech Services if you need us. HVAC, what does the HVAC actually stand for? We got heating, we got ventilating, we got air conditioning. So ventilating side, airflow is very important. Airflow throughout the board. So the air is invisible. Everyone assumes we have adequate airflow, but reality is airflow is 30 to 50% low. We see it a lot. Undersized ductwork is quite a nuisance here, especially here in the Northwest, where we're geared up just for heating. Excuse me. So when we go to put AC on there, and thank you, Jim, for letting me know that. And we are typically undersized when we start going to add heat pumps and variable speed and whatnot. Flex duct is quite a bit less CFM, rated for CFM. I'll show you the flex duct calculator at the end. Duct leakage or high static pressure. I think back to some of my early installations 20 years ago. We were using that gray duct tape with no panduits and nothing else. And I was using a chainsaw to cut holes and stuff. And I think back, man, there's going to be some air leakage. And I've actually ripped out some of my systems that I did years back and sealed everything pretty well. Up to 80% of the leakage is usually at the unit duct connections, right? Like we were saying, porous sealing, hard pipe and pookie sealing is always the best. So air properties must be measured. So we'll go through taking some static pressures and kind of define what that is. These are Mark's. Mark Alkire is in the chat session today. So thank you, Mark, for such great pictures of ductwork you've installed. Just kidding. He did not install that, but and that would work. I mean, that's getting involved with some, that's actually a nice transition. Here's one where they poured the nice concrete pad. That kind of looks permanent, doesn't it? But it's going to work for a little bit, right? They have it landed from the disconnect. They have that concrete pad poured. Again, I've seen some stuff like that that's still out there for years later that maybe they said they were going to remedy it, but they didn't. Gotta love that one. 2-stage. Here's your first stage. Here's your second stage. The things, especially on some of these grow operations where these guys are just putting in their own equipment and making it work, right? They're worried about saving those bottom dollars and they're going to do whatever it takes to get that thing going. Yeah, maybe they wanted a 2-stage unit. It's going to work for a little bit, right? Yeah, I mean, this stuff should always be trimmed and as straight as possible, and make sure that you have a good 90 going into the boots. All right, this could be cleaned up pretty easy. Look at all this room up down here in the basement. So that's, and the pipes even slope downward. These are great pictures of what not to do. I've seen this in crawl space where the guys just don't want to cut it to fit. Flex ducts a lot faster. The good thing is the inspectors are making the guys correct it most of the time. It's an actual install. Mark was on site for where there's having some airflow issues. Actually, I went back on site on this one too. They definitely had to correct everything, move this around, reposition the air cleaner right here. This, again, when we're connecting to air cleaners, we have to have some kind of transition to utilize every square inch of that surface area for that EAC. And we'll go a little bit, I'll show you some graphs for the AccuClean filters and the Clean Effects. So they had to remedy that airflow because it was having constant issues. So is it the equipment or the system, right? Airflow. Airflow will take out a compressor. It'll lead to discomfort in the house, premature failure. So is it the equipment or the system? Everybody likes to kick the equipment pretty quick. We always need to dive a little bit deeper and see what's going on with the ductwork. So what do you do if we cannot get proper performance from the equipment with correct airflow? So you're not going to be accurate. Incorrect airflow, you will not be able to accurately charge a fixed orifice or a TXV system without correct airflow. Everybody knows that our gas furnaces come preset from factory at 350 CFM per ton. So that's the S9V2, the S8V2. We have to adjust the gas furnace to 400 CFM per ton and then put the system in check charge heating or charge mode cooling. Excuse me. So once we achieve a good 10-degree subcooling cooling, or we get pretty close to the pressure curves in heating during heating season, then we can start dialing in and bumping up that airflow if we got a longer heat run, or if they have humidity issues, we can tone down that airflow or airflow noise. Airflow noise, we can tone down the system too. But once we confirm that we have a good refrigerant charge with 400 CFM per ton, then we can start playing with the airflow. And hopefully the ductwork is designed correctly, which static pressures will show that data. So what do? Find out what our airflow is. Why is it so important? Because it's critical to proper system performance. Again, I've always used this analogy with all my homeowners. It's worked for 4 years. Why is it failing now? You take a hair dryer and you cover a brand new hair dryer and you cover the hair dryer back of it by 50%. So you're only pulling in 50% of that air. It'll still work, right? It'll run, it'll operate, but what's it doing? It's overheating those elements. It's overheating that blower motor. That's a good definition of a constant torque. Is constantly trying to work as hard as possible to keep that airflow going over that heat strip, and it will lead to premature failure. So that's another good analogy to tell your homeowners to increase their return air. So airflow formulas, this is a great one. You can write these down. You can text this in. We have forms for you. Some startup sheets with these formulas on there. This does come in handy when you're in the field. So BTU output is your delta T, which is your return air. Actually, your supply air minus your return air will be your delta T times your CFM times 1.08. 1.08 is an altitude factor. In the gas furnaces, they do have the altitude correction factors. I think 1.08 is good to 2,000 feet elevation. So your BTU equals volts times amps times 3.413. BTU equals gas furnace input times efficiency, which we could find those on the data plate. So what is your 1.08? There's my altitude factor. So 1.08 up to 1,000 feet, 1,000 to 2,000 would be your 1.04. I've never been in Western Washington. I had never really had to deal with the altitude correction factor, but now taking calls in Montana and Colorado and parts of Idaho, you may need to correct your altitude factor. It goes for gas valve derating also. CFM calculations, electric heat method. So this is an air handler with your electric heat. So you're going to take the volts, and then you're going to take your actual amperage of the strip heat going in on max, and then you're going to times it times 3.413. Then you're going to divide that by the altitude correction factor, 1.08 times your temperature rise. And then where do we get the 3.413? Because that is how many BTUs per watt. So when they were sizing ACs for agricultural, they would take those bulbs that were providing the UV for the plants and how many BTUs were needed per watt of the light. That's how they're going to size the AC. So that's a good real world application. So electric heat method with 3-phase is going to be the volts times amps times 1.73 times the 3.413. So you're still going to divide that by your temp rise, your delta T times 1.08. And that math works out pretty good. That gets you pretty close to your CFMs. Fossil fuel method, so you're using a gas furnace, you're going to use that BTU input times your efficiency. So if you're 96% or if you're 80%, 80% furnaces, you give me 80. If you're 90 plus, look at your tag or your BTU output. So on the data plate, it will list your BTU output. And everybody, I do go pretty fast, so if you have questions, feel free to ask them in the chat line. Mark is helping on the chat line too to answer any questions.
Jamin, can I make a comment here?
Yes, for sure, Mark.
Yeah, when you're doing this with an air handler and you're trying to find out the whatever CFM you have on a single stage system, most of the compressor blower speeds are the same. So what you're going to want to do is turn up the heat and take off any lockouts so that your electric backup heat comes on when you're running at the compressor fan speed. And then just go outside or, pull the contactor so the compressor doesn't run. So it runs at compressor fan speed, and then you have all your strip heat come on. Then you take your temperature rise with that, without the compressor running, right? And then figure out your calculation at that. That's the only comment I wanted to make.
That's great. Thank you. Yeah, that's without compressor. Sorry. So you're just checking it with the electric heat. So thank you for pointing that out, Mark. Yeah, and this is being recorded. There's a question in there. If you guys got to run, of course, I'd like you to stay here and ask questions while we're doing this live, but it will be recorded and put on Gensco customer. I got a raised hand. I'm going to allow you to talk. Go ahead. You're open to ask a question if you want to.
Yeah. Okay. On your fossil fuel method, your input times your output times your efficiency, would it also work to clock your gas meter to get an actual output?
Whoa. You're way ahead. Yeah, I got a slide in here for you. I'll show you that in a second.
Okay, sorry about that.
No, great question. I love it. CFM couch with electric heat, right? So you got your supply air, got your return air, right? Of course, these should be taken at the unit. If we're taking this at the register, there could be infiltration. We could have some heat loss through the ductwork. Of course, when we start up the systems, we got to warm up all that ductwork or cool down the ductwork. Return airs, you could have multiple return airs. You could have an outside air that's open. So we need the actual air at the indoor unit. I have seen people just take them at the registers, which you don't get a true average of what that indoor return is doing, because it could be 73 at one position. And then if we're actually got an outside air open to 32-degree air, this is going to be registering like 50 degrees. Okay, so it's going to throw you off big time. And if you're pulling in 70 degrees or 73 at one return air, this should be pretty close to 73. And then, of course, multiple stories through the house. Excuse me. So again, this is CFM couch with the electric heat. You got 15 kW, you got volts times amps times 3.413. So we're pulling actual 243. We have 59 amps total to that 15 kW times your 3.413. We have 48,932. So we get divided by the delta T. We got a 38-degree temperature difference times the 1.08 altitude factor, 41.04. 48,932 divided by 4104 does 1192 CFM. So what tonnage do you think this will be? I don't know. Hopefully that's a 3-ton. If that's a 4-ton, we have an issue, right? Fossil fuel. So again, here's our BTU per hour input times efficiency. We'll go over that clock in the gas meter here in a second. 80,000 BTU out input for the furnace. This is a 95% efficient furnace equals 76,000 BTU output. Our delta T is 65, which I do have a slide for an S9V2 where we get that correct temperature rise for the furnace. Again, we are taking this return air temperature right at the unit. Supply, take it a couple feet down if you possibly can, because if we're right above that burner, and same thing with the heat strip, that's going to be a little bit higher degrees than just a couple feet down the duct. And of course, you want, best way is to traverse the ductwork and take 3, right? Because this thing, that airflow is going to be coming off the top of that furnace and kind of bypassing. So this area here might not be the best to get a sample, maybe up here. So 65 times 1.08 is 70.2. 76,000 divided by 70.2 is 1,083 CFM. So this is a great way to actually see what your units are pushing. But technology nowadays, we just cycle through our digital app or on the circuit boards, and we can actually see what the CFM is. Online diagnostics with our Link communicating or our old 1050 communicating systems, we could actually see if it's a communicating indoor, we could see that static pressure, we could see that target airflow CFM, we could see everything what it's doing. So when that filter starts getting plugged, we can actually see that static pressure increase. We can see the static pressure decrease when that filter is changed. So no more of those homeowners telling us, yeah, I change my filter every 4 months. Well, we can actually see it in data when they change the filter. Okay, here's that airflow clock and gas meter. I've only had to do this a couple times, but it is a good method. You got 3,600 seconds per hour. Okay, again, make sure that the furnace, you're going to shut down all gas appliances and you're only going to be running this furnace, right? You're going to be using this 2-foot dial right here. You're going to see that move as your gas is flowing, and just the furnace. Time for 1 foot cubic, approximately 1,000 BTUs. So 75 seconds for 1 revolution. So you're going to clock a timer on 1 full revolution, and in this example, it's 75 seconds for that to do one revolution. So 3,600, that is a 2 foot. So we divide it by 2, 75. So we take 3,600 divided by 37.5 equals 96. 96,000 BTUs we're producing on this example. So again, make sure the furnace is the only gas appliance operating. So we can actually see how many BTUs we are putting out on a gas furnace and airflow. So what is external static pressure? External static pressure is the measurement of all the resistance in the ductwork system that the fan has to work against. Examples are filters. Again, we're just touching on this stuff. So there's a lot more to this. We do have a BDR duct pressure class, and on the Mitsubishi side, we have a duct design class too that goes more in depth. So I do recommend looking at that for future or more knowledge. So examples are filters, grills, AC coils, anything that's going to cause restriction to that airflow. Grills, right? Those nice hardwood grills that we see, those are gorgeous, but they are extremely restrictive. The ductwork, flex duct, is definitely going to add some static pressure. I always like to point out when in Die Hard, when he's crawling through that ductwork, man, I go back, I didn't know anything about it when I first watched that movie. Now I'm like, where's all the screws? There's a bunch of screws in that ductwork that causes resistance too. He'd be all sliced up if he's trying to crawl through that duct. It is the sum. Sorry, I get off subject sometimes. Okay, so static pressure, it is the sum of all the suction pressure or negative in a return air and discharge pressure positive in supply air. So negative in return air, you're pulling in, and discharge pressure positive in the supply air created by the equipment blower. What you'll need to do to take these readings, MagnaHelic. I used to use MagnaHelic. They're great. They're the best form of taking your static pressures. You need a hose with a static tip. If available, you can pull, you can just stick the tube in there, but of course the static pressure tips are the best. Manometer with hoses and accessories. I'll show you a picture of the MagnaHelic and a picture of the digital version. Service facts for the furnace or air handler. You must have service facts. And I tell everybody, please read through those service facts and the install manual when you have free time. Know what's in there. And that's the only way we can for sure dial in our airflow. Right? So here's the graph. Here's higher static pressure, we have lower CFM. Lower static pressure will increase CFM. These are labeled on the side as positive, negative. So you'll have negative going to your load port, which will be the negative return air pressure. The high would be your supply side. And you're going to connect it to, I know our field piece kit has a little magnet disc right here. So you do your 3/8 hole, you slide that in, you point that towards the direction of where the air is coming from, and the magnet holds it in place. So I do like my magnetic ones. Actually, my tools just got stolen, so I need to get that replaced. External static pressure. Here's some outdated pictures. That looks like a really old furnace. Yeah, we need to update these. But this gets the example in there, right? So let's pull the furnace filter out. We can put the filter back in too if you want to know the static pressures or that pressure drop across that filter. But we want to monitor, or we want to take the rating across just the furnace. The coil is external in this case. So we would need to drill probably right here. Dead middle, you could get 3 would be the best way to get the true data and then average them out, but you're going to be drilling in the middle of this. right? And I'll show you in downflow applications, you'll be able to actually slide the probe in the gas line hole. Air handler. So with furnaces, our design static pressure is just for the furnace because the coil is external and you might not have a coil on it. Air handlers has the coil built in, so it is manufactured and tested with the coil in place. So therefore, we're just taking it again before the filter and right above, right? So you got your supply and return, and you're going to add them together for your total external. So again, the air handler has the coil included, so it's tested with the coil. There's a kit. We have that field piece. I do have that one. That's been a pretty good durable unit. You can use that for dialing in gas pressures for the gas valves. There is a kit with the static probes and the little magnetics. That's a great kit. That's a good meter. If you don't have one, get one. So external static pressure. Question is, can we use MERV 13 air filter as a standard filter, or better to use lower MERV? I got a great chart for you, so hopefully you're staying to the end. It goes through actual static pressure and how many CFM per MERV. Air is like water. It takes the path of least resistance. While I'm on that, so same with voltage. So we have a lot of, with electrification, everybody out there, we have higher line voltage. Our max voltage to these outdoor units are 253, but voltage is like air and water. It takes the path of least resistance. So you could have one house on the cul-de-sac getting 267 to the outdoor unit frying circuit boards. So everybody be aware, we have high voltages out there. So check that out to confirm for me, especially if we have some kind of electronic failures in the systems. Confirm that we have good voltage to that house. They're boosting voltages because everybody's getting heat pumps, doing away with gas lines, getting electric cars, solar panels, and all that good stuff. When measuring static pressure in the duct system, lower static means decreased resistance to airflow. So lower static means decreased resistance to airflow. In turn, you will get more air. Higher static means increased resistance to airflow. So we'll have a higher static, higher amperage, higher amp draw on that blower motor, possibly leading to what? More heat and premature failure. So high static pressure restricting airflow. Return obstructions. Well, if it's new construction, did the sheetrocker cover your return air? Do we have an undersized? Did we put in a filter grill and now that filter is extremely dirty because it's 20 feet up in the ceiling and we can't get to it? Filter, again, I can't stress number one reason for many different types of failures are your plugged filter. Coil clean, that's evaporator coils, right? So again, I hear a lot, yeah, they're clean. Well, sometimes you can't see that. The only clean coil is the coil that you just cleaned. I hear a lot, yeah, they cleaned it last year. How do we know, right? A good thorough cleaning, I mean, you can pull that thing out, reclaim the refrigerant, or try to get in there and clean it with detergents and whatnot, but it's a messy, it can get messy. I just had one recently, again, where new construction, the contractor was running it to sheet during sheetrock phase. That sheetrock dust that coats that evaporator coil, as soon as we run it in AC and we introduce moisture into that sheetrock dust, oh, it creates a concrete. So if you guys are doing new construction, be aware, I put it in my estimates that if they ran it during construction phase to preheat the house, they were responsible for me cleaning it and responsible for repairs because you will burn up the blower motors. You'll lose efficiency. They're just doing the homeowner that purchased that home a great disservice to run that. And there's no way around it sometimes. I always heard my contractors say, don't worry, we'll change the filter. Well, yeah, you see, you come You show up to do a startup and that filter is so caked with sheetrock dust. It's just horrible, right? Yeah, that's a great point. If the new construction put the filter at the return air opening to protect the ductwork in the unit. And I know in some cases in commercial TIs, tenant improvements, we were having to cover the ductwork. So to eliminate any kind of, but again, look for your return obstructions. Is the filter and the coil clean? Those are gonna affect your airflow through that coil. And we can actually take a static pressure across that coil to see, is the ductwork sized properly or installed properly, right? So if we're installing a new system and the homeowner wanted a little bit more oomph and we're doing a 4-ton instead of a 3-ton, well, you're probably gonna have undersized ductwork. Again, supply obstructions, are the coil clean? On the supply side, the coil comes into play again. Obstructions, that could be later down the road, did a critter get in there, chew through the ductwork? Did, what is it, up in the attic space and they just had a new roof put on and the roofers were crawling through the attic space and crushed all the ductwork? Or homeowner was running some new speaker wires for a surround system. I mean, those are all things that I've ran into where I've gotten up, I've cleared out the insulation up there and then realized that I had some crushed ductwork that needed to be repaired. And the only way I could tell that without actually going up there digging up, I check my static pressures. And of course, sized properly, installed properly. I don't know how many times the homeowner does not want to pay for that duct modification. And we go abide by it. We let them know. We go ahead and install a system. Sure enough, there's issues, right? Stand by your gut. If you think we are undersized ductwork and all the math is showing undersized ductwork, don't install it without doing it, because that other contractor might go in there and do it cheaper and then have issues and stop answering their phones. They'll eventually call you to come do the repairs and you'll get the service contract. Not always, but I try to do it like that and let people know if they wanted to not install the return, they could go ahead and go with somebody else, but keep my number when they need it fixed. So measuring static, what is a good number? What is a good number for that you should see when measuring static to confirm you got a good system? The only way to know for sure is to compare to the service facts for the unit. Service facts chart up to 0.9. This is important on the fan performance table. So if we start seeing over an inch, like a 1.2, we're off the charts. So keep that in mind. Anything over an inch on the communicating air handlers and whatnot, they will give you a static pressure alert. Furnace stickers say maximum external pressure is at 0.5. This might be getting bumped up in the near future. I know Mark was bringing up, he had seen one at 0.7. So again, always double check your data plates for desired specs or what it's designed for. So as we, 0.5 is a perfect system. Realistically, we see a lot of 0.7. 0.9 is getting scary, because if 0.9 and it's a brand new system with a brand new air filter, what's it going to be after that air filter gets used for a little bit? So rule of thumb, non-variable speed, it'll be 0.4 to 0.6 inches of water column for cooling. Variable speed, we see that 0.7 to 0.9 for cooling furnaces. All limits based on that. ESP is external static pressure. So that's return static plus the supply static is your external static pressure total. Here's a good snippet of an S9V2. And you're going to see that maximum external design static pressure is 0.5 inches of water column. Air temperature rise range. We do, when we're diagnosing heat exchanger and E04 limit switch trips, lockouts, look at that, air temperature rise 40 to 70 degrees. So if we got a 70-degree return air, our max we should be putting out plus 70. So 70 plus 70 is 140. If we start getting over that 140-degree mark, why? we could have some restricted airflow causing that heat exchanger to overheat. And we're limiting out right around 160. Maximum outlet temperature is 170. That means that's what it's tested at, but our limit switch cuts out earlier than that. So between 140 to 160, our limit switches will be set. Thank you, Mark, for this slide. Everybody, if you haven't seen the good, the bad, the ugly, go watch it tonight. This is a great slide that really kind of shows you a full system as simple as it can get, right? So we got our return air grill. We got a couple elbows. We got our 25-foot flex duct. We got a flex 90 in there, not a hard 90. So we should be 20% of the ideal static pressure, 20% for the air filter, supply side 20%. Our coil is going to be about 40%. So the good, all right? So we see a supply duct pressure drop about 0.09, return duct pressure drop 0.08, coil pressure drop about 0.18, filter pressure drop about 0.12 for a total external static about 0.47. We start getting some heavier static pressures. 0.82 is bad, but it's still going to be operating. Ugly is at 1.37. When we start getting over that inch of water column, we're going to possibly start leading to premature failures and discomfort in the home. Now, premature failures are job security, but we don't want to have that homeowner discomfort lead to bad reviews. All pressure drops should add up to less than the fan rated pressure, or you'll have inadequate airflow. So inadequate airflow is going to lead to discomfort, and it's going to lead to premature failure. There's on fieldtechhelp.com, there's a great one, obituary of a compressor. It's a 4-hour refrigeration tutorial class showing you the effects of airflow on the indoor coil, on how it's going to kill that compressor, how it's going to affect that TXV or EEV operation because of poor airflow. So yeah, I definitely recommend watching that one. These are great slides and we can send out. Again, if anybody wants this, go ahead, put it in charts. I can send, we have forms for you to share with your guys in the field, or if you're somebody in the field that wants these forms, they are great to fill out, because once you fill out enough data on these forms, you'll start seeing the issues present themselves as you're filling in the data. So this is a great upflow furnace one. We are taking our static pressure at the supply in between the coil and the heat exchanger, right at the blower motor and before the filter. So B plus C is across the furnace, typically 0.4 to 0.6. That's our design across the heat exchanger and blower motor. Across the coil could be typically 0.2 to 0.3. Now there are designed static pressure for each evaporator coil, but this is a good rule of thumb, the 0.2 to 0.3. So if we wanted to see if this coil's actually plugged, if it looks clean to you, but there's no way you can actually get in there and see the underbelly because the air is flowing this way through it, this is a good way to do it. Just a couple holes and you can see what that static pressure is. And then supply and return, typically 0.1 or less, all the way across your filter. So that's with the filter in. Drop on filter C to D, typically 0.1 to 0.2. And I'll show you a chart on how that affects your airflow through the filter also. Measuring downflow gas furnace. So in downflow, it's pretty much same thing as the upflow. But with these coils, so we got our furnace, we got a heat exchanger right here. There on our coils, our gas is coming into the coil right about here. So we can actually put our probe in that hole. We don't have to drill this hole, and we will be in the airstream before the evap. So keep that in mind. That'll speed you up. We don't have to drill a hole in a downflow application. Let's just use that hole on the gas side of the evaporator coil. Okay, gas furnace PSC. So single speed tap. We do have a couple different speed taps. This is a PSC motor, constant. Let's pick a 3-ton. This is as simple as it gets, because all we're going to do is we're going to check our static pressure. So if we're on our medium high blue wires on our speed tap heat at 0.5 inches of water column, we're going to be running 1065, but this is a 3-ton, so we want about 1200 CFM. So look at that, 0.3 on high speed black, we're about 1200 CFM. So you can see we have to know our static pressure. Then we can move our speed taps to change on the different set of windings on that blower motor to change. And we got to constantly monitor our static pressure in order to confirm what our CFM is. But as Department of Energy keeps pushing us everything more efficient, they'll probably do away with the PSC motors. There'll be some that still have it, but not used for airflow. Here's our S8X1. This one is out of the 60,000 BTU. Everybody knows S series are the shorties, 34-inch tall. 8 means that it's an 80%er. 1 means it's a single stage. 2 is a 2-stage. We got a 60,000 BTU, 3-ton blower motor. So at 0.5 design static pressure, we change these taps through the menu select buttons on the circuit board. Tap 5 default is 1123. So again, the good thing with the S8s and S9s, we can actually change these CFM settings on the fly, so we don't have to de-energize the system. Keep in mind, if you have a dip switch that you need settings, you're going to have to cycle power. You're going to have to kill the power, change your fan setting, and re-energize. And then, again, take your static pressure to see what your actual CFM is. Gas furnace with the ECMs. Again, here's some dip switch settings. It goes back. You're going to have to kill the airflow or kill the power. 400 CFM. So you're going to have switch 1, 2, 3, 4 off. And then you're going to come over here. You've got 0.5. We're going to be 1200 CFM. So these are the dip switch units. S8V2. So here's the S8V2, 80% variable speed, 80,000 4-ton. We're going to have a 2-stage. So our default is medium low. So target airflow is 865. So at 0.5 static, with the temp rise of 38. So we're going off of there. We can be at medium low. We're actually 861. 864 is most common with the 0.7. And then our high speed, medium low. Again, we can change these settings. At 0.5 is 1315. This is our minimum for our gas heat, by the way. So if we had keep in mind, this is for gas heat. This is airflow for the gas heat side. If we're hooking up a 3-ton heat pump to this unit, what is our 3-ton heat pump going to need for airflow? Because it's a different setting. It's going to be 1200 CFM, right? So this for gas heat, our maximum minimum airflow is 1330. For heat pump, it's going to be running 1200. So it'll be different airflow for the outdoor unit that's pre-programmed in there. So you'll have a different value when checking your heat pump airflow. S9V2, again, here's our 2-stage. We have a minimum 814. If we have the 0.5, let's go to 0.7 static. we're going to be producing 838 CFM. We should have about a 42-degree rise. High side, where you're looking at about 1,000 CFM. Again, we can change these speed taps on the fly through the board. Measuring air handler static. Again, the coil is built into this, so it is tested with the coil. So A to B across the coil, there is some drop for the electric heat too. So we're going to be 0.2 to 0.5. Supply and a return is typically 1 or 0.1 or less. Drop on the filter, typically 0.1 to 0.2. That could change on the different filters. Keep in mind, I have seen where these returns and maybe on the inside of these units where the sound liner has actually came unglued and they didn't have any pins. Watch for that. A good way to detect that without tearing apart your ductwork is take your return air plenum static pressure, because it'll flop in place in idle. So if you were to take this filter out and you're looking in, you don't see anything wrong. But as soon as you start that blower motor, it'll suck into the filter. It could appear further or further upstream in the return. Yeah, those are hard ones to find sometimes. But if you're taking your static pressure and you're getting a 0.6, 0.7, you know something's up with that return. So again, it's all about eliminating questions and concerns. So if you can pinpoint a high static area, you know where to address your static pressure. GAM2, TEM4s, you don't see too much of these. There's still there. I mean, there's a lot in the field, but not on new construction. Speed taps, you got your 230 volts. You got medium, high, or low. At a 0.5, you're running about 1504. So again, you're going to be changing out your speed taps on your air handlers. Again, that's minimum heat speed tap without heat pump, with heat pump. GAM5. Again, all these charts are kind of the same. So you see, that's what we wanted to, everybody just to be aware, all these service facts. You're going to have an external static. So you're going to take your external static and you're going to compare it to whatever speed tap you're on. There's usually a default that's marked. So this one's default speed tap 4 at 0.5, you're at 1556 CFM.
Jamin, can I make a
10-6.
comment?
Yes, please.
Yeah, on that, like on the speed tap fan motors, if you look at those as the external static rises, okay, the airflow drops, right? So, but with a true ECM motor, variable speed, as the static goes up, the airflow, like on the next slide, the airflow would stay pretty consistent. Like here we've got, let's look at this 3-ton, like at the CFMs over here. Yeah, you got 1147, 1149, 1141, 1123, and 11 if you're on low speed, right? See how as the static goes up, the airflow stays pretty good, but your wattage goes up. That's what why the true ECM variable speed motors, they can overcome marginal ductwork, but they can't overcome bad ductwork. And that's just what I wanted to point out on these charts, is that when the true ECMs, the airflow will, try to stay up, the motor will ramp up through the internal torque, amperage, and RPM calculation that it makes. And that's all I wanted to mention. Thanks.
Thank you, Mark. Again, Mark has years of experience and he's pointing that out. It's bringing attention. Higher amperage, higher wattage will lead to premature failure, right? So these ECM motors, they will keep that CFM, but your wattage goes up. What costs money to operate? Your watts. You pay per watt. So higher static pressure means costlier electric bill because you're using more wattage. So that is something to check out too. If you hear of a homeowner complaining of high bills, they didn't have to pay this much on their old system. It could be their airflow is being restricted, therefore we're at higher static and we are using more, especially if they're running it 24/7. So when we first got variable speeds on the scene, the salesmen were saying, oh yeah, it'll overcome poor ductwork, but it'll overcome slightly poor ductwork, but there is a additional cost to that and for long run settings. So that's something you could have an open discussion with your homeowners too on why they want to add that ductwork. So thank you, Mark, again. Okay, so here's the temp 8. So you got these buttons on the furnaces too. We're going to cycle through 7-segment displays, going to give us our target airflow. Again, I can't spend too much time on this, but what I do like to do whenever you guys call in and you're in the field, I'm going to have you open up the service facts and we're going to go through that flow chart with you. I'll go through it with you the first time. That way, second time, third time, fourth time, you guys understand what's in there and how to decipher the data that's being displayed on that 7-segment delay. We got a J10 electric. This is the flow chart I like to go through with you guys. Again, our gas furnaces will become preset for 350. So you're going to see 350 per ton right here. And then you're going to press the select. So you're going to go list. It's going to go down the flow chart, press select to go right, choose, press list to go back and save. So list. If that was at 350, we'd press select till we got to the 400 and then press list again and it'll save that 400. So if you guys do have questions while you're on site, please give us a call, text service 253-620-8282. And I'd love to go through that with you. You're always going to put in your outdoor tonnage. If it's not communicating in a 24-volt system, we have to plug in that outdoor tonnage. TAM 8 service facts, again, same stuff that we've been seeing, right? So you're going to see this constant same graph. I think we went through enough of them. There are settings in here for the constant CFM mode or constant torque mode. Again, constant torque mode is going to get you higher wattage to achieve that CFM. TAM X. Now TAM 9 is phasing out. We got the TAM X. TAM X is going to be 24-volt compatible or the new Link software. So with the new Link software on online diagnostics, we can really see that what that indoor airflow is doing. We can see the static pressures too. So we're using the blower motor static pressure to truly see what that system's doing through the air handler. The furnace is coming, where we'll be able to see the static pressure and gas pressure in the modulating Link furnaces. So pretty excited about that. But the amount of information these TAM X Link systems are providing is insane. I love it. We can actually see when that filter is getting plugged up. Finding the solution. So we got downflow gas furnace, right? So these are ideally what we want to see. So total external static pressure is 0.75. We could have symptoms, could be the coil freezing, your furnace is tripping limit. So we could see iced up coil. We got a 0.35 right here and a 0.4 across the furnace. We're well over the 0.5. Sorry, I jumped the gun. I thought we were showing the ideal ones, but this is finding the solution. We got it issued tripping limit switch here. So why are we tripping the limit switch? Looks like our 0.1, so we got a 0.3 over that filter. Filter too small. Boy, we see that a lot too. I'm going to show you a chart on 20 by 20 by 1s, our max CFM. If I go out to a job site or I see a 20 by 20 by 1 on a 4-ton system, I'm going to go right towards that filter sizing. Filter media is too restrictive. That's going to drop back to our MERV 13 air question. Higher the MERV, the more restrictive. Here's another one. We got a 0.1 on the return. We got a 0.25. So we got 0.15 across that filter. Ooh, look at that, 0.55. on that as a vibrator coil. Let's see. So we got a total external static pressure of 0.8. Again, same symptoms. Our coil could be freezing, trapping air, and our furnace is tripping limits in EO4. So we're overheating the heat exchanger. Why? We got another plugged, dirty coil possibly. They ran it during new construction. Undersized coil. We have seen that to where I've seen some 2-ton coils installed on 3-ton systems. So we got an undersized coil we just can't handle the airflow over it. Let's see what this one is. Another downflow gas furnace. We got 0.5 on the return. 0.55, so the filter is okay. Our total external static pressure is 0.75. So again, the same kind of symptoms, coil freezing and his furnace tripping limit switches. We can't breathe. This one, the return air is restricted. So again, once you memorize what those pressures should be, good rule of thumb, we're going to be able to detect what's going on with our return. Did it get crushed? Did sheetrock cover? Do we have a filter return air grill? Is the return air on the ground and people moving around their furniture and accidentally covered a return air? Seen that a lot. Seen that a lot. All right, so here's another scenario. Total external static pressure of 0.8, 0.25. Looks like our filter's good. We got a high supply. Again, showing the same symptoms but our issue is in a different spot. Supply air is restricted. So 4 holes in your system checking static can tell you a lot. All right, total external static is 0.4. So we're kind of close on this one, but we have light airflow. So this is kind of opposite of having restricted ductwork, right? But it'll show you the same symptoms: coil freezing, furnace tripping limits. It could be a wrong unit for your ductwork. So what if we have 5 ton of ductwork with a 3-ton furnace? So oversized ductwork is not good either. Don't see that too much, but we have seen where there's too big a ductwork and we don't have enough static pressure to work efficiently. That could be blowers plugged too. We always want to check amperage. We want to see what that actual blower motor voltage is getting. Secondary could be plugged on a 90+ furnace. We have a primary heat exchanger that's pretty wide open, but that secondary is kind of tight. If man, I have found a raccoon in one, so that was plugging up the secondary. That's kind of gross. Bad or wrong motor. This does happen once in a while. We get a wrong motor put in there. Again, with the S8V2s and the TAM-X air handlers, they won't need a personality module. Everybody knows that the personality modules in our systems are what controlled the fan speed, told it what horsepower it needed to be, how many CFM it's designed for. The TAM-X and the S8V2 do not come with personality modules. They come with every model number plugged into that board. So if you get a savvy homeowner, Boeing engineer, because I've dealt with a lot of those Boeing engineers, I know them, they're going to be reading through something and they understand a lot of it. So they think they want more air for some reason. They're going to make that a 3-ton furnace. They can tell it that it's actually a 5-ton furnace right now. So if we do have airflow issues in those S8V2s and the TAM-X, first thing I'm going to do is probably check we have the correct model number in there. Check in the app or through the CDA, the 7-segment display on the circuit board. So unit, this one, we're under static pressure. Unit's not capable of developing the necessary static. Looks like we got an upflow, total external static 0.7. Our supply plenum's at 0.45. Same thing, coil freezing, furnace tripping limits. We got an over temp. This one, we got our supply air is restricted. What's this one doing? We got 0.05 negative on the return, 0.15. 0.10, not enough air. Total external static pressure 0.25. Same symptoms. Got a wrong unit, undersized. Blowers plugged or dirty, so it's not ramping up. Oh, this with the TAM9, TAM-X's, this is critical too. If we do not have enough air, it will not fire up heat strips. We'll get a heat strip alert. So keep that in mind. We had one where we had a 4-ton system with a 8x24 ductwork, 60% less airflow than what it needed. They changed out the electric heat because they thought it was a heat strip failure. No, it was a return air issue. They had to add a return to get that enough CFM to energize electric heat because these units are so smart, it's protecting itself. So again, bad or wrong, unit is not capable of developing necessary static. Again, coil freezing, furnace tripping limits. This one, the return air is restricted. So we could have plugged filter, we could have that sound liner came detached. I know I'm going through these pretty quick, but you guys get the idea on how important it is to check our static pressure. So here's that chart. This is going over 1 inch. Okay, so we're straight out of Columbia. Gensco makes Columbia filters, right? So this is information for Columbia filters that we provide. You can see, let's use a 20x20x1. It's not even rated for 500 feet per minute. That's only good for 833 CFM at 300. And it's got a 5.67 pressure drop. 2 inch, well, you can see 20x20 is only 833. 2 inch, 20x20x2, now at 500 feet per minute, which that's what we're rated at, 1389. So can we use a 20x20x2 on a 4-ton unit that requires 1600 CFM? No. So I look at that quite a bit. There's a 20x20x4 is still only rated for 1389, but your pressure drop in surface area, your pressure drop got better. I'm sorry, this is the surface area. Again, another side that shows the pressure drop right here. So that is our surface area. 4-inch filters have more surface area, so it's less restrictive. Most disposable 1-inch poly filters are rated at 300. So the 1-inch filters are rated at 300. And it's rated at 0.07 pressure drop. The 2 inches are at 0.1. Okay, so this is from Flanders. These are AccuCleans and Clean Effects. This is important because when using these are great for filtration, but look at this pressure drop on these. We get a lot of them where they're doing an FD17 on a 4-ton and a 5-ton system. You don't even have ratings on here, so you can't use them for 4-ton and 5-ton. So this is a good chart to see what you can actually use on those 5-ton systems. You want to put in the biggest possible, because look at this 0.39 pressure drop. So you definitely want to oversize these as much as you can to get a good filtration, and a good airflow. We just added this one in. This is an S8V2 link furnace. This is a great picture of ductwork. Please, please, please build transition to try to get as much as that filter as possible. It's really bad when we see these plenums come straight down and we're panning off 4 to 6 inches of that air filter. We're restricting airflow and we're not actually using that filter to its best. This is through link zoning. So this is a great illustration. We can actually dial in our static pressure on link zoning, and because we're using the blower motor static, but at 0.7 inches, we're at 1884 static on this unit. At 0.9, we're actually producing more CFM, but that's torque's going up. And then we can adjust it to 1.1 and look how much CFM, 2,472. So the higher static, we're telling that blower motor to ramp up, use more wattage to produce more CFM. Then over the airflow, the larger surface area equals lower pressure drop and better filter performance. So larger surface area equals lower blower watts and improved efficiency. So we get better comfort and improved efficiency. So let's increase those filter sizes. That's not going to hurt anything. Finding the problem, checking static pressure drop, check the static pressure drop across the fitting. This can come into play, right? These square throats are horrible for airflow. So these are poor because the airflow kind of skips over here. If we have a square throat, square heel, we want some kind of turn vane in there to direct that. Of course, radius heel, radius heel, radius throat are the best for airflow. Minimize that static pressure. So velocity should be 600 to 900, and that's out of the ACA manual. High velocity, we could have noise issues, return air grill humming. So you could get harmonics in that return air grill where we can try to open those up as much as possible to get some airflow over it. Air whistle at the grills and registers. Comfort complaints, cold air. We could be picking up cold drafts from the window. So that's high velocity issues, improper air distribution, low velocity problems. If we don't have enough air, it's not going to comfort the area as good. Poor air distribution, stacking of air. So it's just not throwing it all the way and reaching the ceiling for full circulation. So air distribution, where and how the air distributed is almost as important as the quantity of air. So this is often disregarded in design, but we want 1 CFM of primary air movement per 10 to 20 CFM of secondary. So we have to compromise our locations due to furniture, decor, practicality, window settings, right? So they used to have all the supplies on the interior of the room and the returns on the exterior. Now we've had the returns on the interior of the room and supplies on the exterior. So know where your supply and returns are. Of course, these registers with the dampers, you know, people are always thinking they're not going to heat that room, so they're going to close that up. Be aware that's going to increase static pressure and could possibly lead to discomfort. So we want to make sure when we're starting up the system, make sure we got all the registers open. Let people know, don't close up too many because that's going to create an issue. There's some high velocities. I like these grates, so keep that in mind. You get some harmonics with these, take your tongs and kind of open these up a little bit more, or get a stiffer grill if you got a sensitive homeowner to that. I didn't hear them at first, and then I kind of grew to be able to hear that and avoid a nuisance call back when the homeowner is complaining about it. Yeah, noise solutions, line of sight, return air grills, attenuation. Yeah, you've heard that before, haven't you? Noise generated and trunk turbulence, velocity. Sometimes the dampers will rattle, so I recommend definitely tighten those all the time. Noise generated at grill. Here you go again. It does sound like that, but it'll be a higher tone sometimes too, to where only the wife can hear it and the husband thinks she's crazy, right? But I'll go in there and I'll actually hear it too. So she'll feel better, and then the husband knows she's not actually crazy. Duct popping, that's a big one, right? So if it's undersized, that's what the cross brake is in there for. You'll hear that return air, suck it in, it'll shut off, it'll pop back out. So that is a crazy noise if it's loud and in the middle of the home. We want to be aware we might have some static pressure issues for undersized ductwork. I mean, leaks can cause dirty, unconditioned air to enter the residence. If it's not, especially if it's a return and it's not sealed, you're going to get a lot more dust and possibly insulation in the airflow. I always recommend the air filters be right at the furnace, just in case we have air infiltration. Leaks can cause health and IAQ problems. Boy, I saved these people. They were having big issues and they had the duct board. And it was just a critter had gotten in there. So they had that insulation in their airstream for 4 years. She always had issues. We went in, tore out all that ductwork, replaced it with rigid metal, re-insulated it, put in a nice filtration system. And in 6 months, she had called me saying, thank you so much that we found that. She had been feeling much better. So that house was really affecting her health. You guys go to your local branch. They should have these. This is a great air duct calculator. We can go off of our round, our rectangular duct, our friction and velocity. You can size these accordingly, 1.0 to 0.8 to 0.5. Air duct calculator, here's another version. I mean, you got your round duct right up here. You got your rect duct down here. We have your static pressure. Flexible duct. Again, this is a different calculator for the flexible duct. I'm going to show you the difference. Look at this, rigid. Here's rigid, right? So this is a 14-inch round, or 10 by 17. Or 8 by 22, right? At 0.1, we're 1,000 CFM on 14. And at 0.8, we're about 900 CFM. So let's just go off of 0.1 for this example. We're 1,000 CFM. So 14-inch flex duct at 0.1, look at that. We're at like 750. That's a lot of airflow that we're not calculating for if we're using the wrong instruments to measure our airflow. So if we're having airflow issues, we'll be able to see something wrong with it if it has flex duct. Gensco Tech Support Quick Form. If we are having issues on site, we're going to send you this. We're going to ask you to fill it out. Give us as much information as possible. It's going to give us a lot of details. So again, I use this as a tool. I had a different version when I was running my HVAC and managing my install and service techs. This is a tool. You give it to the guys that don't know how to fill it out. Help them fill it out. If they need help filling it out, call Gensco Tech, or maybe we can get a class to show them how to gather the information. First time, it's hard. Second time, it gets a little bit easier. Third time, where they're starting to see patterns. Fourth time, fifth time, sixth time, you will start seeing the problem as you're filling in the data. So this is a great tool to educate your brain. When I started out, I had my little notepad I'd carry in my pocketbook. I'd write down as I had perfect systems, outdoor temperature, pressures, gas line temps, super C subcool. I'd refer to those perfect temperatures when I had issues. Again, this tells a lot. These quick charts has our CFM. You know what? I missed that slide. I must have not had it. You guys save this website, fieldtechhelp.com. That's straight from Train Factory, American Standard Factory on tutorial videos. I like to send out my tutorial videos. Give me a survey. And also, biggest thing in this is please scan this, leave in the notes section or comments, put in 3 classes you guys would like to know more information about. And maybe we can do a class on that.